So for our first video in the rate of chemical change module, we are going to talk about particle theory and how it affects the rate of reaction. The kinetic particle theory explains the properties of solids, liquids, and gases. There are energy changes when changes in state occur. The particles in solids, liquids, and gases have different amounts of energies. They are arranged differently and move in different ways. Solids, for example, have fixed shape and they cannot flow. This is due to the fact that particles cannot move from place to place. They also cannot be compressed or squished, as the particles are close together and have no space to move into. Liquids flow and take the shape of their container as the particles are free to move around each other. They cannot, however, be compressed or squashed. This is because the particles are close together and have no space to move into. Gases, on the other hand, flow and they completely fill their container due to the fact the particles can move quickly in all directions. They can also be compressed or squashed as the particles are far apart and have space to move into. That was just a general overview of particle theory and its differences in different states. The table shown quite nicely summarizes that for you. So overall, in this presentation, we are going to talk about how the changes in surface area, temperature, and concentration affects the rate of reaction, and it will link into particle theory. For any chemical reaction to happen, the reactant particles must collide with each other, and the particles must have enough energy to react. So, if we start with surface area, you can see that by decreasing the particle size of a reactant, there are more surfaces that the collisions can take place on. The smaller the particle size, the faster the reaction. So when we talk about surface area, we do generally tend to think about lumps, which is represented by figure A on the diagram on the left, versus powder, which is represented by figure B of the same diagram. So for any given mass of a solid, large lumps have smaller surface area to volume ratios than smaller lumps of powders. If a large lump is divided or ground into powder, its total volume stays the same, but the area of the exposed reactant surface increases. Therefore, the surface area to volume ratio increases. Now, when we look at lumps versus powders, the greater the rate of successful collisions, the greater the rate of reaction. If the surface area to volume ratio of a reactant solid is increased, more reactant particles are exposed at the surface. Therefore, the frequency of successful collisions between reactant particles also increases. Therefore, the rate of reaction increases. Now, as previously mentioned, for a successful collision to happen, particles must have enough energy. Now, if we go from a lump to powder and increase the surface area and therefore increase the rate of reaction, this doesn't mean that we have an increase of energy in the particles. The energy of the particles stays the same. However, due to the frequency of collisions increasing, the frequency of successful collisions also increases. All three states of matter expand when they are heated. The atoms themselves do not expand, but the volume they take up does. So, for example, when a solid is heated, its atoms vibrate faster around their fixed point. The relative increase in the size of solids when heated is therefore small. For example, metal railway tracks have small gaps in them, so that when the sun heats them up, the tracks expand into the gaps so that the tracks don't buckle and break. When we look at liquids, they expand for the same reason as solids. However, because the bonds between the separate molecules are usually less tight, they expand more than solids. This is the principle behind mercury in a glass motor, as an increase in the temperature results in the expansion of the liquid, which means it rises up the glass. Molecules in gases are further apart and weakly attracted to each other. The heat causes the molecules to move faster, as heat energy is converted to kinetic energy, which means the volume of the gas increases more than the volume of a solid of a liquid. However, gases that are contained in a fixed volume cannot expand, and so an increase in temperature results in an increase in pressure instead. Continuing with temperature. So if we increase the temperature of a reaction, this increases the rate of reaction. So at higher temperatures, the particles can collide more often and with more energy, which makes the reaction take place more quickly. If we look at the graph to the right, you can see the effects of both high and low temperatures on the rate of reaction. The pink line represents the higher temperature, and it has a much steeper gradient and the reaction levels up quicker. This is because the particles have more energy and are moving around quicker and are therefore more likely to collide with each other and cause a successful collision, making the reaction go up faster. And finally, concentration. If you increase the concentration of a reactant, there will be more of the chemical present. More reactant particles moving together allow more collisions to happen, and so the reaction rate is increased. The higher the concentration of reactants, the faster the rate of a reaction will be.